Good afternoon and a very warm welcome to all. My name is Dr. Mansoor Nellikal and I'm an enterprise fellow with PSDI, that is Physical Sciences Data Infrastructure, and I'll be chairing today's session. If you're new to PSDI is a UK-wide initiative building a digital platform to make physical sciences research data more accessible, reproducible, and easier to share. Today is actually the second session of our webinar series, From Project to Platform, New Resources of PSDI. So this series showcases high quality tools and resources developed through the PSDI's 2025 funding call with the aim of introducing them to a broader community and connecting them with potential users. In today's webinar, focus on high quality scientific data resources for excited state modeling and materials discovery. We are pleased to have Malin Zollner from the University of Strathclyde presenting when TD-DFT fails benchmark 1500, a multi-reference excited state dataset for organic semiconductor discovery. Let me introduce the speaker. Malin is a research assistant in chemistry at the University of Strathclyde. Her work focuses on developing data resources for organic semiconductor discovery, particularly to support data-driven modeling and machine learning applications. She completed her MChem in pure and applied chemistry at Strathclyde in 2024 and has since developed a strong focus on the intersection of computational chemistry and AI-driven material discovery. In today's webinar, Malin will introduce the benchmark 1500 and dataset and demonstrate how this dataset can be used to analyze time-dependent DFT limitations and support machine learning-driven discovery of organic semiconductors. Over to you, Malin.
Thank you very much. Yes, I'm Malin, and I will present the BenchmarkSet1500 to you that I worked on under Taharani Matiaram, who was the person with the idea behind this project. And I want to start by talking about the project aim was why we wanted to do this. So the main aim was to create a multi-reference excited state benchmark set for organic semiconductors. And yeah, I want to break this down a little bit, why we focused on this specifically. So the first thing I want to talk about is why we focused on organic semiconductors. So organic semiconductors are of interest for research because they can be used in a variety of applications, such as organic light emitting diodes. So we see that in screens and phone screens, or for example, switch screens. They can be used in solar panels, so interesting for the renewable energy sector. And they can also be used as biosensors, so that's interesting for the healthcare industry, or as organic lasers. They're also more sustainable than traditional semiconductors because they do not use rare metals and instead use abundant elements. They can also be produced under milder fabrication conditions, which makes them more sustainable as well. And they are flexible, so we can get flexible screens, like what you can see on the screen here as well, a picture of it. And this means they are less brittle and prone to breaking. And we can produce wearable electronics. So that's, for example, of interest in the healthcare industry again, where the patient comfort is important for example, sensors. And they can be used on curved surfaces because of their flexibility. So we can, for example, get solar panels on curved car roofs. And then from a chemistry standpoint, they are easy to fine-tune because of all the structural variations. So we can fine-tune them to exactly the application that we want to use them in. And now going back to the project aim, we know why we focused on organic semiconductors. And now I want to talk about why we focused on the excited states of organic semiconductors specifically. So the excited states are important because they determine important properties, such as the optical gap that I'm showing here. So this is the gap between the ground state and the first excited state. And this determines the absorption window. So for example, this is important in solar panels where we would want this to line up with the UV spectrum. And then also another excited state property, the oscillator strength. They control the absorption intensity, and you can think of it as, for example, the brightness in OLEDs. The higher the oscillator strength is, the more likely it will absorb and emit our light, and therefore be brighter the more gets emitted. Talking about applications where excited states are important, so as mentioned earlier, the OLEDs, for example. So the first generation OLEDs utilized the emission from the first single state down to the ground state, the fluorescence, and harvested that as the emission as the thing that's shining in our devices. But due to spin statistics, only 25% of spins are singlets. So we're missing out on the 75% of spins that are in the triplet state, which does not emit bright light. So then the question came about, can we maybe harvest those dark triplets to increase the efficiency of our OLEDs. And there are several methods. One of them is, for example, the thermally activated delayed fluorescence, TD-DFT, where we use reverse intersystem crossing to upconvert those triplets back to singlets, which can then be emitted brightly again and harvested. And then similarly, there's inverted singlet triplet gaps, where the triplet gap is higher in energy than the singlet, so we don't need the thermal activation to do the reverse intersystem crossing down to the singlets again. And technically, this is forbidden chemically, but there have been molecules found where this is the case. So now it's of interest in the research community, can we find more molecules that do this? And then another application is anti-Kircher molecules. So these are molecules that do not emit from the first excited state, but from higher excited states. And that means, they can emit high energy light, so we can get blue and UV emitters. And again, this is technically forbidden chemically, but there are cases like this that can potentially give us the blue and UV emitters, for example. So going back to the project aim, now that we know where we focused on excited states of organic semiconductors, why a multi-reference data set and what is multi-reference? So traditionally, TD-DFT has been used to compute excited states, and it is widely used because it is a computationally cheap method, which means that it is suitable for high throughput screening. And it is also relatively reliable for smaller organic molecules. But there are cases where TD-DFT breaks down and is not reliable. And these are cases where strong state correlation and degeneracy is important, molecules with double excitation character, and inverted singlet triplet gaps. And you might have noticed that these things are relatively closely linked to what I mentioned earlier, the applications. So, for example, the inverted singlet triplet gaps cannot be predicted by TD-DFT at all, but they are very interesting for our emerging technologies. So these are not just rare edge cases where TD-DFT breaks down, but important molecules that are of interest for our organic semiconductor research and going forward. So this is where then the multi-reference comes in, because this is a solution to the problem. Multi-reference methods can describe near degeneracy, inverted singlet triplet gaps, and double excitation. And the commonly used one is KCCF, which adds static correlation. So it can treat if there are multiple states occupied and there's not just a single state. And then on top of it, an FPT2 is often used, which adds a dynamic correlation on top of the static correlation of KCCF. So it treats the electrons not just as a mean field, but actually individual electrons. So now that we know that there was a problem and we have a solution, it might surprise you that so far in the literature, there have only ever been a handful of molecules described being calculated by multi-reference methods for organic semiconductor research. So this is where then we come in with our aim to create the first benchmark set using multi-reference methods for organic semiconductors to create a large-scale benchmark set. And now I'm going to talk about how we did that. So we started with an initial database of around 40,000 molecules from the Cambridge Structural Database, and they computed TD-DFT excited state energies, which were computed by Omar et al. And then once we had this database, we filtered it down further to get exactly the molecules that are of interest, where we think TD-DFT does not describe them very well. So these are molecules with small singlet triplet gaps that might not actually be small, but inverted, but TD-DFT cannot predict that. Or molecules with double excitation character, so we looked at the ratios between the singlet gaps. And then once we had those molecules, we optimized their ground state using B3lib631G star. And then with that optimized ground state geometry, we calculated the excited states using KCCF and FP2 that I mentioned earlier. And that gave us our excited state database of around 1,500 molecules. So this is the benchmark set 1,500. And we have the properties for the first and second singlet and triplet energies, and the first and second oscillator strengths. So the properties that are important that I mentioned earlier for the applications. And then also now that we have this database, we also applied it to show what you can do with it. So this is just an example, but we screened for specific applications for inverse, TD-DFT, and anti-Kircher molecules. And I will talk about that too. So, but let's start by talking about the database. What does a database look like? So here, first I'm showing the database size, what kind of molecules, how big they are. And generally, there is more smaller organic molecules with mostly carbon atoms and hydrogen atoms. The heteroatom count is relatively low, around 5. And yeah, the atom count lies usually somewhere between 20 and 60. And when you think about a benzene ring already has 12 atoms, for example, you can tell that it's mostly smaller molecules. And the molecular weight shows this as well. Then another thing of interest to look at for this dataset is the rotatable bond count and the ring count, because it is known that organic semiconductors are usually more efficient if we have loads of aromatic rings and if they are relatively rigid. So we can see that here that the rotatable bond count is more around 5, more leaning towards the lower end. Whereas we have a high ring count, especially considering that our molecules are relatively small. And then we also looked at the similarity between the molecules, how diverse is our data set. So I used the average Tversky similarity. And you can think about it like this, that if it's around 0, that the molecules are not very similar to each other at all. And if it's around 1, they are identical, the molecules in our data set. So you can see it's like hovering somewhere around 0.4, 0.5-ish, most of the molecules in the data set. So that means that it's like medium diverse. So considering that it's small organic molecules, you can see it's relatively diverse for this specific family. So it actually is widely applicable, and we can draw conclusions not just for one molecular family. Yeah, and then here is the database statistics when it comes to the computed energies and oscillator strength. And I'm comparing the different theory levels here. So TD-DFT being the lowest accurate one, CAS-SCF being the intermediate one, and FBT2 being the most accurate one in describing the excited states. And you can see maybe generally that CAS-SCF overestimates our energies pretty consistently compared to the other theory levels. I also want to point out that TD-DFT is very much underestimating our first oscillator strength. But I wanted to zoom in more on this, the differences between the theory levels. So this is where I'm coming to the next section. Ask the question, when are lower theory levels sufficiently accurate in describing the excited states? Can we maybe get away with lower accurate methods? To this, I compared the correlation between 2 different theory levels and the different properties. So here, first of all, I'm comparing TD-DFT to CAS-SCF, so the lowest accurate method to the intermediate one. And you can see that only the first triple energy has a high correlation. And by high correlation, I mean a correlation coefficient above 0.8, whereas all the other properties are below it. And we can see a similar trend when we're comparing TD-DFT to FBT2, so the highest accurate method. And you can see that this time both triple energies have a high correlation, but all the other ones are still not very well correlated. And then when we compare the intermediate one to the highest accurate method, we can see a different picture. Now, especially the oscillator strengths are actually really highly correlated and nearing 1, and both triple energies are highly correlated. But I want to specifically point out the singlet energy that is not highly correlated. And that is specifically interesting because you could technically say, oh, if I'm only interested in oscillator strength, for example, I can get away with using CAS-SCF. Or if I'm only interested in triple energies, maybe I can get away with using TD-DFT. But a lot of the time when you're investigating those molecules for specific applications, the singlet energy is very important, and it is usually gaps you're looking at. And singlet energy plays a significant role in most applications. So generally, singlet energy is very important. So I would say I would not recommend a lower theory level if you want to accurately describe excited states overall. Yeah, but this was an analysis on the full data set, which brought me to the next question. Maybe I can zoom in even more. Are there maybe specific molecular families where we can get away with using lower theory levels if it's not the whole data set? Through this, I compared the 2 different theory levels. And I first decomposed my molecules into Venus-Merkur scaffolds to find specific families within my dataset. And here I'm showing the results for the most common families in my dataset. And I'm showing how much they agree with each other. So if it's around 0, that beigey color, the two theory levels agree with each other, whereas if it's very blue or very browny red, then they very much disagree. And I want to first highlight the ones that are highly correlated, the scaffolds. So we have scaffold C and I here. Whereas on the other hand, when comparing TD-DFT and FP2, they don't agree with scaffolds B, D, G, and H. And B is an acyclic scaffold, so there's no ring that the BEMS Merkle scaffold could decompose to. And then similarly, I compared CAS-FCF to an FP2, so the intermediate to the high accurate one. And first of all, what you can see is that generally they agree a lot closer with each other. It's a lot more beige. And when we're looking at the ones with high agreement, it is molecules that had low agreement earlier. And yeah, it is smaller molecules, very rigid nitrogen-containing heteroatoms, compared to the ones with low agreement, where we see they are a lot bigger and have rotatable bonds, are a lot more flexible. And it is unsurprising because in FP2 has dynamic correlation, which means bigger molecules with more electron density are probably accurately described by CAS-FCF. Then, now moving on to summarizing this section a little bit. So we can say that some properties are well captured by lower theory levels. For example, the oscillator strength by CAS-FCF, but singles are not. This can be maybe detrimental for your analysis of excited states. So overall, we cannot say that you can get away with TD-DFT. The full manifold is not sufficiently accurately described at lower theory levels. And then when looking at molecular families, we can say at lower cost theory levels are sufficient for specific molecular families, which are usually the smaller, more rigid heterocycles. So yeah, overall, this leads to the statement that can be made that lower cost theory levels do not provide reliable values across the full screening data set. They can be used for pre-screening, like we use TD-DFT for pre-screening, but if you actually need the specific values, you will probably require higher accurate methods. That led me to my next question. If we cannot get reliable values, can we maybe at least get reliable classifications? So can lower theory levels still recover an FP2 level application candidates? So if we screen for specific applications, can at least the lower theory levels still identify the candidates, even if it's not the exact energy value? So this led me to screening, and the first thing I screened for was TD-DFT molecules. So here I looked at a small singlet triplet gap, but still positive gap, and then also relatively bright oscillator strength, because if we actually want to use this in an application in OLED, for example, we want it to be bright and actually emitting light, so we set the oscillator strength to be above 0.05. And what you can see here, theory level identified TD-DFT molecules and how much they agreed with each other. So the first thing you can see is that there are a lot of molecules that only NaFPT2 identifies. So 55 molecules are only identified by NaFPT2. And CAS-FCF identifies some of the NaFPT2 molecules as well, 28. So this means generally at least CAS-FCF identifies some molecules, whereas TD-DFT does not agree with the other theory levels and does not identify a lot of molecules under these screening conditions. So we can generally say that maybe you can get away with CAS-FCF if you don't want to find every molecule, if you just want to find some molecules. But if you want the full picture, you probably require an FP2 to find TD-DFT candidates. Then I did a similar thing for invest candidates molecule. So here we set the singlet triplet gap to be negative and then also have a bright oscillator strength. Here you can see that NaFPT2 is the only theory level that actually identifies any invest molecules. So I even had less strict oscillator strength requirements in my filters, and there was never any point where the other theory levels identified invest molecules. So only NaFPT2 can identify invest molecules, and yeah, you require this. And here I'm also showing the molecules, the ones with the lowest single triple gaps. And I wanted to point out that I found it was interesting that most of the invest molecules had this chemical tetrafluorylane. I don't know how to pronounce it. this as a scaffold within the molecule. Yeah, and then I also screened for anti-Kasha molecules. So here we looked at the singlet gaps and the ratio between it, and we basically want the gap between the ground state and the first singlet set to be small in comparison to the one between the first singlet and the second singlet. And we also want right oscillator strength. And here we can see a slightly different picture. The lower theory levels identify a lot more molecules, and we actually find 10 molecules that all three theory levels identify. But there are still a lot of molecules that only NFP2 identifies. But yeah, if you don't need all of the TARDIF molecules, maybe you could get away with lower theory levels here for anti-Kasha screening specifically. But generally, again, 82 molecules are only identified by NFP2. And then now I'm going to summarize this and what we have learned. So first of all, TD-DFT is not sufficient for important molecules, but can be useful for pre-screening, like we used it as well. And then you identify or look into your molecules more that you pre-screened and filtered down. And multi-reference datasets are required for accurate description. And now that we have a dataset, a multi-reference dataset, we can get guidelines. For example, we saw that accuracy depends on specific structural families and properties, and this dataset could be used for theory level guidelines. So to figure out those specific families and properties where you could maybe get away with lower theory levels. And then this dataset can also be used for application screening. So it can screen for desired properties like I did with the INVEST, TARDIF, and anti-Kasha molecules. And then I want to touch on the future work as well, what can be done with this dataset in the future. So the first thing is we can follow the recommendations that this dataset gave us and the candidates that it found for example, INVEST, TARDIF, and anti-Kasha, and validate these using experiments or high-level quantum chemical calculations. And then we also provide a GitHub workflow that is openly accessible. So this dataset can be expanded further under the same consistent chemical conditions, computational conditions. And this means that then the application, screening, structure, property relationships, and guidelines can be expanded further if the dataset is expanded as well. Lastly, the dataset can also be used for machine learning. So, for example, transfer learning, where we take a lower theory level and transfer it to a higher theory level. Regression task, where we predict NFP2 properties. Application classification, similar to what I did with the screening for INVEST, but you introduce new molecules that were not in the dataset before and classify them using machine learning. And then you can also use generative AI once you've identified those interesting scaffolds from your interesting INVEST molecules. For example, you find the scaffolds and then generate new molecules from that using generative AI. And this concludes the section on my presentation. But I now want to give a quick overview on the dataset and how to access it, give a quick tutorial. So the dataset is available on the Data Collections PSDI website. And yeah, this is what it looks like. And you can find our benchmark dataset by going to communities. So I've already prepared that. This is what it looks like when you click on communities. And when you scroll down, you can see the benchmark set here. And then there are lots of other interesting communities as well that you can check out. And yeah, when you click on the benchmark community, this is what it will look like. You will find all of our molecules here, and they are named after the Cambridge Structural Database ID. And we'll have a look at the entries later, but first I want to just quickly show the About page. So that's a little introduction of the dataset as well. And also a link to the full dataset as a CSV file, which I will talk about later as well. And also the GitHub workflow that I mentioned in the presentation as well. And I will show more later as well. So going back to the entries now, this is what it looks like. And then when you click on an entry, when you click on it, this is what it will look like. So here you will find the Cambridge Structural Database ID. And then when you scroll down, here you will find the link again to the full dataset, which I will show later. And then also here are the files. So we uploaded the Gaussian output files of the excited state calculations, so you can even extract more data if you want, and also the ground state optimized geometries of each molecule. So this can be of interest, for example, for machine learning, where you can derive some descriptors from this. And then when you scroll down even further, here's a link to the publication that the molecule was first identified in. So here, for example, this was the publication this molecule was first identified. And then when you scroll down further, here is the actual properties that we calculated, the excited state properties. Here the singlets, triplets, and oscillator strength, and then both for CASXCF and MEF-PT2. And when you scroll down even further, here are some molecular identifiers, like the CCGC ID, SMILES, INCHI, molecular formula, and there's also a link out to the CCDC entry for the specific molecule. So this is what that looks like. And then when you scroll down even further, here is some metadata on how we computed the excited states. So for theory levels, we use active space, basis set, and what software. And then here on the right-hand side, you can also export this data, which might be of interest. For example, in JSON, but there are loads of other options as well. And yeah, this data is all open access, so you are free to use it as long as you cite us. I now want to talk about the full data set. So this is what it looks like when you click on the link, but you can also find it through the AI-ready dataset community that's also on the PSDI community website. And here's a little introduction to the dataset. Then a little bit a description about all of the different columns in our Excel spreadsheet, which I will show as well. Yeah, all of the things that are basically in the single entries as well. You can find here's a little view of the file, and here you can download it. And yeah, I can show you, this is what it will look like. So it will have the ID as well, then the different identifiers that are also on the individual entries. And then here you can find the calculated energies. This is then machine learning ready. You can compute descriptors from it and use the energies and oscillator strengths as targets, or whatever you think you can do with it. And then, as I mentioned earlier, we have that GitHub as well that we link to. So this is how we constructed the dataset. You can find that here. I provided some geometric files as well, so you can have a test run and see if you get the same results as me. And then here are the 4 steps. And then here's also a README file with the specific steps explained further, but I'm also going to explain them now quickly. I have prepared everything to show you exactly how to do it. I just need to log into my HPC. Hopefully it won't take long. Okay. So here, this is what I prepared. So the first thing is that when you download it, this is what it will look like. So here you have your 4 steps, and then you have the geometric files that I gave as an example. If you now want to get your Gaussian input files, which is the first step, what you can do is first navigate to your folder, and then you can run the code like this. Now you have 2 options. You can either directly select the specific XYZ file to compute this for, or you can drag in an entire folder, which I will do here with our 3 examples. So now you can see that XYZ file read and then written were the com files for Gaussian. So if we reload this, now we can see that here we have the Gaussian submission files now, and then here are also the submission files for your HPC, which you would have to adjust in the code for your specific HPC that you want to run this on. And then once this is done, yeah, this is what it will look like after step 1. And then the step 2 is the Gaussian error. So this means that once all your calculations are run, I have here prepared some files. Once the calculations are run, this is what it will look like. You will have your log files, but Gaussian often runs into common errors that have common fixes. So this is an automated script to detect those errors and try the most common fixes. And yeah, it will automatically create new input files and submit them. So here I added some files that I know will have errors, so I can show you what that will look like. So first we need to navigate to that folder again. And then we can run our code. Like this. And yeah, now you can see it sorted for the error files, and we can have a look here. So it now created log files folder with all the successful calculations, then also a folder with all the unsuccessful calculations. So here, for example, the error L9999. And then it also created new Gaussian submission files for those errors, trying to fix them. And here also for your HPC, again, submission files for those errors. And then going to the next step, once all of your Gaussian calculations were successful, so you have a folder here with log files of successful calculations, and you have a folder with checkpoint files. You don't have a folder with formatted checkpoint files yet. I have put that in because I don't have my checkpoint files anymore. I already transferred them all to formatted checkpoint files. But let's just pretend that there's only a checkpoint folder. And then again, we can run this by going to our folder and then running our Python code. So it will first read the checkpoint file, transfer it to formatted checkpoint file, and then once it has the formatted checkpoint file, it will transfer it to XYZ optimized geometries. So it creates a folder here with the optimized XYZ geometries from the formatted checkpoint files. And then from this optimized geometry, we then create Orca input files for our Excel state calculation. And then similarly here, we have the submission files for the HPC again. So now then the last step is, once all the Orca calculations were successful, we can move on to step 4, where we extract the results. So again, to do that, quickly change into that folder like this, and then we can run the code by typing in the name of our Python code. This will now create results file. This might take a while because Orca files are quite big, and it also adds some metadata to it that I showed you earlier, like the number of atoms, the inches and smiles and so on. Hopefully this won't take too long. So here now the results were extracted from the Orca output files. So we now get an Excel state spreadsheet, and I already have a prepared open here what it looks like. So similar to the thing that you can also find on the AI-ready datasets, it has the same columns, but there's also an added column of job CPU time in case you're interested in that. So yeah, this is basically how you use the dataset, how you can download it from the PSDI dataset collection, and also how you can use the workflow. And that's all from me. Yeah, I'm happy to take questions if anyone has them.
Thank you very much, Malin. That was an interesting presentation and the demo was really good. Let's now open the floor for questions. How sensitive are the results to the choice of what type of multi-reference method you use?
So the two multi-reference methods I used were CASA-CF and NEFP2, and you could see that there were quite significant differences when we compared to theory levels as well, even though they're both multi-reference. So I would say they are very sensitive to it. And even if you don't want specific values, even if you're screening for applications, we get very different candidates from the different multi-reference methods, yeah.
Are you expecting that dataset to be static one on the PSDI, or are you expecting others from your community to add to it in the future?
For now, it's a static one, but maybe we could discuss it if anyone is interested in contributing in the future. Yeah.
Cool. Thank you very much. Thank you again, Malin. We have our PSDI resources live now, the ones which Malin showed in your talk, and we have a couple of other resources. So if you are new to PSDI, please feel free to take a look at the website, and we have various resources and tools which will help you in your research. So do explore them. We also have a couple of events and webinars lined up. So as I mentioned earlier, this is a webinar series, and this was the second in the series. We have like few more sessions which were the outcome of the 2025 funding call. So the session 3 is on flow battery community. Session 4 is on SIM-NMR data. Both the registrations will be open shortly. So if you keep an eye out on our events page, you can see once the registrations are open, and you can register them. We also have a workshop. It's an in-person workshop at Southampton. So the transitioning from FAIR to AI ready data in the physical sciences PSDI and Alchemy workshop. It's on 16th of July. So the registrations are open now. You can see the details on our events page. We are also on social media, all the major platforms. So you can follow them for updates, and all our previous webinars you can find on our YouTube channel. These are our social media pages, and please do follow them for updates. And let me thank you, Alan, once again for giving a wonderful webinar, and thank you all for attending. See you again in the next webinar.